Okay, I'm going to work an example of a refrigeration cycle, and one that's a little bit different, maybe just to give you some idea about how to work through a problem that is a little bit different. So I'm going to just talk over the screen here, and I hope that will be adequate. But what you should see here is a schematic of a refrigeration cycle that has a condenser and a compressor, and so that's very conventional. We've seen that before, and an expansion valve. But what becomes different is everything from 4 to 1 across here and below. Here we see 2 evaporators and a couple of more expansion valves. So what this machine is designed to do is to provide refrigeration at 2 different temperatures. Evaporator 1 is at a low temperature, evaporator 2 is at a higher temperature, at 2 different temperatures with a single compressor. So there's one circulation loop for the working fluid, but there are 2 paths that the working fluid passes through. Some of it goes through evaporator 2 and some of it goes through evaporator 1. So the particulars we have for this problem is that we're going to use refrigerant 134A, that the temperature of the evaporator 1 is given, that is at minus 18 degrees C. So now remember that in the evaporator we will have a 2-phase mixture here at state 5, and we're going to evaporate it completely. As you see here, saturated vapor leaves each evaporator. So this occurs at constant temperature, a phase change at constant temperature, and therefore this is also a constant pressure. But this temperature is given as minus 18. The second evaporator, the pressure is given rather than the temperature, and we can maybe figure out what kind of temperature this operates when we go and look up the properties. But the pressure is given at 4 at 320 kPa. And what else do we know? Oh, the condenser pressure is 1000 kPa. So we know all the pressures. Pressure 2 and pressure 3 are equal. We assume there are no pressure losses in the devices other than these expansion valves. There's a pressure drop from 3 to 4. So pressure 4 and 7 are going to be the same. There's a pressure drop from 7 to 8. So pressures 1, 8, and 6 and 5 are all going to be the same. And there's a pressure drop from 4 to 5 here. Okay, well, it might be a good idea to take a look at TS diagram and see if we can anticipate what this cycle is going to look like. We're given quite a bit of information. We know that we have saturated vapor at state 6. I mean, it's given here. So we have saturated vapor at state 6 and at state 7. We also know, well, I guess it's not stated explicitly here, but it should be. Let's state that saturated liquid leaves the condenser. And that's consistent with the standard assumption for a refrigeration cycle, that we're going to fully condense this fluid up here. So we know this state, we know these are saturated vapor states, and we know these are all throttling processes. And remember about the throttling process, we have an enthalpy, constant enthalpy process, isenthalpic process. So these are constant enthalpy. So I think we pretty much know all these states, but one thing to look at ahead here is if we consider that this region right 1, 8, 6, that's really a mixing process where we're going to take whatever we have at state 8 and mix it with the saturated vapor coming from the evaporator 1, and that's going to give us the inlet condition to the compressors. That's really, I think, the only state that we don't know here, and we'll have to consider that in turn. But let's look at the TS diagram. I've made a little bit of a preparation for looking at that to see what we have. So I'll have to flip back and forth here a little bit, and let's see if we can. Oh, I should have come up with this ahead of time, but let's make a nice little dot there, and we'll call that. Okay, so what do we have? We have saturated vapor. It's going to be hard to drag that. He wants me to stretch it. I don't want to do that. There we go. That's coming out of our low temperature evaporator. That's our state 6. So I think we can fix that. And then what else? That 6 mixes with 8. Well, what's 8? Well, we've got saturated vapor coming out of the evaporator 2. So what does that look like? Evaporator 2 is at this intermediate pressure, the middle pressure. And so we have saturated vapor coming out at 7. So let's find that. That's going to be, I think it's going to let me work with that a little bit. There we go. That's our state 7. Now, what happens between 7 and 6? Excuse me, yeah, 7 and 8. Well, we have a constant enthalpy process. And I don't quite know what a constant enthalpy process looks like on here, but I do know that it's going to increase. It's going to increase the entropy, and it's going to have constant enthalpy, as we said. So my state, I'm going to get rid of that guy because I don't think I need him. Let's copy this one right here. And that's going to be our state 8. Okay, so that's 7 to 8 across that. It's constant enthalpy. Now, I guess I probably need a little bit more room here, so maybe I should have changed it up. But here's my point. 6 and 8 are going to mix together, and then that's going to give me state 1. So where's state 1 relative to 6 and 8? Well, when I mix this at the same pressure with this at the same pressure, I'm going to get something that's in between here. And exactly where in between, I don't know. But my state 1 is going to fall right in between these two. And so that's going to cause a little bit of a complication as far as this drawing, I think. Let me try to shift 8 up here a little bit further away. And I don't know if that'll clear things up or not. And maybe bump this guy over. Okay, but anyway, in between there will be the state 1. So when we mix two substances together and they're staying at the same pressure, they're going to be on the same pressure line, but it's going to be a mixture of those two things. So we're going to mix 6, which is saturated vapor, with 8, which we don't know exactly where it's going to fall out here, but when we mix them together we'll get 1. So how do we go from 1 to 2? Well, that is isentropic. That's it says the compressor is ideal. It should say compressor, not compressors. There's only one. And that means it's going to be constant entropy. So this is a TS diagram. So constant entropy is straight up. How far up does it go? Well, it goes from the low pressure, 6 and 8 are low pressure, 1 is low pressure, to the highest pressure. So we're going to connect these lines. We're going to connect like that. And just to kind of keep everything uniform here, we'll copy that format and throw it on that line right there. There we go. So what state number do we have there? That one is going to give us numero dos, number 2. So let's copy that guy, state 2. There we go. So we got 1 to 2 is going straight up. Now what happens? 2 to 3 is condensation at constant pressure. So the pressure is constant going from 2 to 3, and we said, I added on, saturated liquid leaves that condenser. So saturated liquid then will be State 3. Let's throw that on there. Give him a number. And then from here it should be pretty straightforward. What do we have? Expansion valve, constant enthalpy, expansion valve, constant enthalpy. So we can find where these states fall on here. So we're going to go, let me find that constant enthalpy line. And let's make that a dashed line. Why do we show a dashed line, by the way? The dashed line indicates that it's an irreversible process and we don't know the exact path. In this case, I guess we do know the exact path because it's isenthalpic, it's constant enthalpy. But you see that it's going to be constant enthalpy 3 to 4, but then it's going to continue constant enthalpy 4 to 5. So these states lie on the same constant enthalpy line, and they would look something like this. Here we go. So those would be states 4 and states 5. Okay, so I think that's pretty much our whole cycle there, and it gives us the big picture of what's going on. Now, to proceed with the analysis, what we're asked to do here is find the mass flow rates 7 and 6. What is that? The mass flow rate 7 is in this evaporator 2, and mass flow rate 6 is in this evaporator 1. Notice that it is given, I didn't write on the left-hand side here, that the cooling capacity for each of these evaporators. So this is a design problem to determine how much cooling do we need to have. I mean, how much flow rate do we need to have to provide a certain amount of cooling. So we can find that now because just since we can draw a TS diagram and we can show every state, we can find the enthalpy for each of these states, and we can figure this out. So let's piece it together. So what do we have? We need to know things. Let's just find all the enthalpies. Let me make a list. I'm going to need to know H1 and S1, and S1 is equal to S2. And then I can find, yeah, maybe we can just go like this. So this is equal to the enthalpy for R one enthalpy of the saturated liquid as a function of temperature. That's what we were given at state 1, and this is R134A. So the temperature that we were given was T1. Well, sorry. Yeah, I can't do that at all, can I? I just got through telling you that 1 is actually a mixture of 6 and 8. So I need to start with the 6 maybe. And I think I actually gave that as 5. Let me go up here and get us some numbers to work with. So, yeah, that's all we've got. 5, 4, and 2. And we know some of this other stuff. So let me figure this out. This is not H1. This is H6. There we go. And let's get H7. How much is that? Well, that's equal to the enthalpy of the saturated vapor. Yeah, I screwed up that first state as a function of the pressure. We were given the pressure there, and the pressure we were given was P4. Yeah, let's fix this. This is not saturated liquid. This is saturated vapor. There we go. And the units here, kilojoules per kilogram. Okay, and then where do we go? We need to find out this state 1, but we can't do that until we know these mass flow rates. What am I talking about? Well, to find out the mixture 1, we need to know the flow rate and the state here, and the flow rate and the state here. And then we can find out what this mixture is. So let's look at these individual evaporators and answer the questions, what are these flow rates? So for the intermediate pressure evaporator, we need this enthalpy at the inlet, and notice that H3, H4, H5 are all the same. So how much is H3? H3 is indeed H liquid as a function of pressure for refrigerant 134A, and that's based on, I think I called it P2. Yep. So if you wanted to, and maybe it's a good idea to put H4 and H5, to just put that that's equal to H3. And when we put some names on here, that'll all clear up. Okay, so now we know those. Let's figure it out. Q dot, what do we want to call that at P middle? We can call it 2, yes. Here's evaporator 2, and here's evaporator 1. So Q dot at evaporator 2 was given to be 2 tons. Great. 2 tons. What good is that? Well, I think I told you before that there are 12,000 BTU per hour in a ton, but that there were also 3,412 BTU per hour in 1 kilowatt. So this should give me the approximate capacity in kilowatts for that intermediate pressure evaporator. So now this will allow me to find the mass flow rate that was requested, and that is that the mass flow rate at what did I say, 7 is what I called it, m dot 7. It's just going to equal to Q dot 2, yes, divided by the enthalpy change across there, which is H7 minus H4. So where in the heck is that coming from? Well, it's kilograms per second. Where is that coming from? That's just coming from a control volume on evaporator 2. That we've got enthalpy coming in here, we've got enthalpy going out there, here's how much energy is being picked up, and that's the m dot times delta H for this control volume. I guess we could put a control volume on there. It'll take a second, of course, because when I put a control volume on here, he likes to make it look like that. But really, let's get rid of the filled in part and make it a dash line just for fun. There we go. So if we look at what's crossing the system boundaries here, we have H4 coming in. I guess we really should maybe squeeze that bad boy up a little bit. There you go. So it's really just this part, but it's still state 4 that's coming in there, state 7 that's going out, and the heat transfer that's coming in. M dot H4 plus Q dot is equal to M dot H7. And I didn't write that. I just went to the shorthand version here. So we repeat exactly the same calculations down here, except this is going to be Q dot 1 for the low temperature evaporator, and he said the cooling capacity there is 3 tons. So we put 3 tons, and And that's how much we're dealing with. And then this m dot, it's not m dot 7, this is the m dot 6, I guess we called it. And it's not going to be q dot 2, it's going to be q dot 1. What's the delta H for that evaporator? Well, it's H6 minus H5. And of course H5 is equal to H4, so that doesn't really matter, but H6 minus H5. And we don't know what q dot 1 is. We can sort that out. Perfect. So those are the mass flow rates that are required in order to give us the evaporation across the cooling capacity that we want here. And how did we do that? Of course, we just put a control volume on this one, and it looked like that. So anything that crosses the control volume boundary comes into our first law equation. We've got the heat added, the m dot H5 in, and the m dot 6 H6 out. And implicitly we've used the fact that m dot 5 equals m dot 6 because it's just steady flow through there. Okay, we're making progress. Now we do need to find that mixture 8 before we can find out anything about the work. In other words, we need to know the actual state, I'm sorry, not state 8, state 1. We need to find the actual state entering the compressor, and then we can do our isentropic analysis of the compressor and then figure out how much heat is rejected. So let's put a control volume on the mixing T. At what was that? 681. 681. So that means, what am I talking about? I'm talking about putting a control volume right there. So we just need a small control volume, smaller still. But really, there we've got 6 coming from here, 8 coming from here, and they go together to make 1. There's no external heat transfer, so if we write our first law equation, it's just going to say that H1 is equal to the mass average m dot 6 times H6 plus m dot 7 times H8. Looks like I've got to do some, what happened to H8? Did we not, oh, H8 is equal to H7. We just kind of fell off the wagon here. Let's add some more in here. H8 equal to H7, sure. Because we had enthalpic constant enthalpy across this expansion valve. 7 and 8 have the same enthalpy. So we've got that. I need to add that into the list of states, and somehow I didn't get m dot 7 in there. So now this is not correct because this has to be divided by the total mass flow rate, which is m dot 6 plus m dot 7. So I haven't written the whole equation out here, but I think you can see that what this says is that m dot 6 plus m dot 7 times H1, that's what comes out of that mixing valve, the combined mass flow rates times H1, that's equal what goes into that control volume, which is m dot 6 times H6 coming from state 6 plus m dot 7 times H8 coming from state 8. So, well, he says it's found a little flaw with my parenthesization there. Yeah, I need to put parenthesis in here and not to put parentheses down there. There you go. So the numerator divided by the denominator, I get 244. And what I promised you is that that state 1 was going to lie in between states, what do we have, 6 and 8. So just to kind of check that, H6 is 239, H8 is 251, and H1, which is in between there, is 244.27. Okay, so now what do we need to do? We've got to, state 1 is defined now by the enthalpy that we just found and the pressure, which is this lower pressure. What is that pressure? We didn't find it yet. Good grief. Well, it's the saturation pressure at minus 18 degrees C. So we've got to find that pressure and that enthalpy, and those two things will tell us this state. We can find that entropy at state 1, and then we'll use S1 equals S2 to find state 2. Now you can do this with the tables. It's going to be kind of challenging because these are all going to be odd numbers. So let's see what I'm talking about. Note that P1 is equal to the saturation pressure for R134A at the given temperature of T1. Why do I not have a T? Oh, it wasn't T1. T5, I guess it was. Let me double check that I had the right. Yeah, T5 is the temperature that we have, the minus 18. So that's an oddball number right there, and that's not going to be in your superheated tables. So what that means is you have to interpolate, double interpolate if you will, between two pressure levels in your tables to find pressure equals 144.5, and then interpolate again on enthalpy to find the corresponding value of S. But with these Excel add-ins, there's a function that will give me the entropy as a function of the pressure and the enthalpy for refrigerant 134A. So the pressure is P1 and enthalpy is H1. And it tells me that entropy is 0.96211 kilojoules per kilogram per degree K. So what? Well, I have to use that entropy to find the enthalpy at the exit of the compressor. So I'm going to use a function that gives enthalpy as a function of pressure and entropy for refrigerant 134A. The pressure is my high pressure P4, and the entropy is that one we just found, PS. So I mean, conceptually that's a pretty straightforward operation. In other words, I'm going to take S and P at state 2 and find that, but finding S1 is a little tricky with the tables, and then interpolating at 1000 kPa with that S is pretty straightforward to find this H2. Okay, so with those properties, I think we're just about done. Yes, because we know all the states now. We found state 3, 4, 1. We've got 7, 8, 1. We know everything. So now we can start to answer the last of these questions, which becomes what is the work required for the compressor? Well, we should be able to find that pretty quickly. W dot for the compressor is just the enthalpy increase across there, H2 minus H1, but we have to multiply by the mass flow rate. What's the mass flow rate through there? It's the total of m dot 6 and m dot 7. Okay, so we're coming up with 2.112 kilowatts. And what else did we need to find? I think just the coefficient of performance. Is that all it's missing? Yes. The COP. The COP for this would be a little tricky, but meaning that we've got cooling at 2 evaporators. We would consider the total cooling capacity 2 tons plus 3 tons divided by the work, and we'd consider that to be our COP. So the COP for cooling we would just write as Q dot 1 plus Q dot 2, those are both in kilowatts, divided by W dot for the compressor. And I thought I had that in there. W dot for the compressor. Huh? Oh, I see. Well, maybe I did. I just mistyped it. Okay, so it's about 8.3, which is very excellent. So, all right. So the things they asked us to find are here. We can highlight that a little bit. The work required for the compressor, the mass flow rates. And we can dress them up a little bit if you'd like. So, okay. That's it for this example. It's just been an example of a different kind of refrigeration cycle, and hopefully give you the idea that you can take something that you haven't seen before, apply the basic principles for this type of cycle that we have learned, and just take it piece by piece to break it down and analyze it and find whatever information is requested. It's also been a pretty good exercise about going from the hardware and state descriptions to a TS diagram and how you can piece that together. And that's also often very helpful in trying to solve some of these problems.